Section 16.6 deals with polysaccharides. So when we take many monosaccharides and we link them together, we get what are called polysaccharides. So first we're going to take a look at the type of polysaccharides that we find in plants, namely starch. And starches, which you've probably heard of, they're found in things like potatoes, are the storage forms of glucose that we find in plants. So what a starch is, the storage form of glucose found in plants, they are polymers of alpha-linked glucose. And by now you should know what is meant by alpha-linked glucose. So a little bit more about those linkages in the glucose or between the glucose molecules. So it says here that if the links are only 1,4, so if they're only 1,4 alpha links, the polymer is linear. So it has a linear shape to it, and that's called amylose. And amylose makes up about 20% of what plant starch is. So amylose usually assumes a helical configuration, so that means it forms a helix, so it kind of does this turn like this. Anyhow, with 6 glucose units per turn, and I have that on another slide that I'm going to address in a few minutes here. So if our polymer, if it has both alpha 1,4 and alpha 1,6 links, then the polymer structure is branched, and I'll show you what that means in another slide, and we call that amylopectin, and that makes up about 80% of what starch is. So amylopectin is highly branched, so these 1,6 links are the branches. So when we have the 1,6 links, those are the branches, and those branches are approximately 20 to 25 glucose units long. So let's take a little bit more detailed look at the structure of amylose. Now I told you that it was an alpha 1,4 linkage, and this picture comes directly out of our book. And what does the alpha refer to? Well, here's carbon 1 on one glucose molecule, and you can see that the glycosidic bond is going down. Now I realize that there's an angle in here, and that kind of looks like there's an extra carbon here, but in fact there isn't. The reason that they draw it like this with this angle in here is not to confuse you, it's to actually show you the amylose, it's kind of got this linear shape like that. So you have the alpha 1, and then the glycosidic bond is formed between carbon 4 on the next glucose molecule. So again, it has this helical form. So if you were to take your hand and put your thumb up like, I'm not really much of an artist, but if you put your hand up like this, your fingers are going to go in this direction, right? So we call this a left-handed helix, okay? So the left-handed helix, anyhow, like this. And when you look at the number of glucose units per turn, so if I start here and then I say, okay, well, here's a full turn, going back to this slide here, it says there's about 6 glucose units per each one of those turns in that helical configuration. So there you go. So that's what amylose looks like. So amylose, what's the take-home message? The amylose is a polysaccharide formed from alpha-D-glucose, and the linkages are alpha 1,4. And amylose makes up about 20% of what starch is. If we compare the structure of amylose, and this is kind of a more accurate representation of what amylose is because it doesn't have that little angle shown here. So again, we have our alpha 1,4 linkage. What amylopectin, the difference between amylose and amylopectin is this branching here. So we have a branch, okay, and we have these branches coming off. We have these branches every 20 to 25 units, and those branches are alpha 1,6. And what that means is that the branch is alpha coming off of an anomeric carbon, and it's between carbon 1 and carbon 6 of another glucose unit. So that's the alpha 1,6. So again, the main chain is just these alpha 1,4 linkages, just like an amylose, but in amylopectin, we have these branches coming off like that, the alpha 1,6 branches. So let's move on and talk about what glycogen is. And glycogen is actually pretty close in its structure to amylopectin, but it does have a big enough difference that we can differentiate between the two. And glycogen is actually the major glucose storage polysaccharide or carbohydrate that's found in animals. So when animals store glucose, they store it in the form of glycogen. And glycogen has a lot more branches than amylopectin does. So it's a highly branched chain polymer like amylopectin, but it's got more frequent branching. You remember the branching in amylopectin was about every 20 to 25 units. We had a branch on it. But in glycogen, we have branches about every 10 units, so more frequent. And glycogen is stored in liver, and it's also stored in skeletal muscle tissue. And if you've ever studied biology before, you'd know that glycogen from the liver and from the muscle cells is broken down by a peptide hormone known as glucagon. Anyhow, we'll talk about that in another chapter. So moving on to cellulose. Cellulose is actually the most abundant organic molecule in the world. So therefore, it is definitely the most abundant polysaccharide. So cellulose is the major structural polymer found in plants. So if you've ever wondered what holds a flower up, the flower stem is very small, but there must be a lot of strength in that flower stem or in a blade of grass, to make it stand up. And what provides that rigidity in the walls of plants is cellulose. So it is a linear homopolymer comprised of beta D-glucose. So if you remember, amylose had alpha D-glucose units. Well, cellulose has beta D-glucose units, and they're linked beta 1,4. And I have a picture of cellulose coming up. So the repeating disaccharide in cellulose is called beta cellobiose. And what happens is that animals, the reason we can't go, nourish ourselves on some hay or something like that is because we lack the enzymes that are necessary to hydrolyze cellulose. So actually, animals like termites or cows or goats, they are actually able to digest cellulose. And what they do is that they have bacteria in their digestive systems that can actually break down the cellulose into sugars that in turn can be metabolized by these animals. But again, we lack the enzymes to be able to do that. So cellulose in our diet is just a source of fiber. So here's the structure of cellulose, and you'll notice that I have all of my glucose units linked here together, and that they are linked in a beta 1,4 fashion. So if I look at carbon number 1, the glycosidic bond is going up, therefore this is beta. And then it's bonded to the hydroxyl, or the glycosidic bond, I should say, was formed from the hydroxyl on carbon 4 on the neighboring glucose molecule. So what do you need to know about cellulose is that humans are unable to digest cellulose. It is made from glucose units, but beta D-glucose, and the linkage is a beta 1,4 glycosidic bond. So those are the main things that you need to know about cellulose. So this slide just has a little comparison of the structures of glycogen and amylopectin. And you'll remember that amylopectin and glycogen are quite similar in their structure, and that they both have chains of alpha 1,4 linked D-glucose molecules, so like this, okay? And they both have the alpha 1,6 branches coming off like this. But the difference is that the branching in glycogen is more frequent. So you remember that it was about every 10 units, whereas in amylopectin, the branches are much farther apart. They're about every 20 to 25 units apart. Also, you'll notice here that the branches in glycogen are shorter. And the branches in glycogen and the branches in amylopectin are quite a bit longer than they are in glycogen.